So the last time we finished talking about combustion reactions and how we could predict a balanced chemical equation for a combustion reaction simply by knowing the starting material it was going to burn. And this level of predictability, where we have to put oxygen on the reactant side and CO2 and water on the product side, makes combustion reactions very useful for chemical analysis. And it allows something that's known, not surprisingly, as combustion analysis. The way this works for combustion analysis is that we take some sample and we put it on a stage or something inside a furnace and feed oxygen in and then just burn the sample. And on the right side here, after it's burned, it produces CO2 gas and water gas, and we run it through some trap that will collect all of the water, and some additional trap that will collect all of the CO2. So we have some water absorber and some CO2 absorber, and that allows us then to measure the mass gained by the CO2 or the water present, both of those. Now, what that allows us to do is actually back calculate what the original formula of the material that we burned was. So say I had some material, I knew it was a hydrocarbon of some kind, but I didn't know what the formula was. I could put it into my combustion analysis, burn it, and collect the masses of water and CO2 and then back calculate. Well, how do we back calculate exactly? Well, let's look at this process, and this will help us to determine the back calculation for determining first just the percentage of each element present in the molecule, and then finally we will work our way back to the formula. So if we start with the mass of CO2 produced, what I will first do is, using the molar mass of CO2, I'll convert that to be moles of CO2. Now, I know that there's only one carbon atom per molecule of CO2, which means that there's 1 mole of carbon atoms per mole of CO2. Using that allows me to convert from moles of CO2 to moles of carbon. And I know that all of the carbon in CO2 came from my original sample. So the moles of carbon that I've determined here must be the number of moles of carbon that were in my original sample. If I then use the molar mass of carbon, I can convert that number of moles to a mass, and that allows me then to determine the mass of carbon that was present in the original sample. Now I'm going to do something similar with water. All of the hydrogen from water comes from the original sample. It doesn't come from the oxygen, certainly, that's fed in. All of the hydrogen comes only from my original sample. So I take the mass of water that's produced and I convert that to moles using the molar mass of water. Now, there are 2 hydrogen atoms per every 1 water molecule, which means that there are 2 moles of hydrogen atoms per every 1 mole of water molecules. Using that molar equivalency, I can now convert from moles of water to moles of hydrogen that were present in the original sample, since all of the hydrogen from water came from the original sample. Now that I know moles of hydrogen, I can use the molar mass, or just the atomic weight really, of hydrogen, and convert from moles of hydrogen to mass of hydrogen in the original sample. So now I know the mass of carbon and the mass of hydrogen in the original sample. Now that I know that, I can determine the mass percents, or the percent by mass, of each element. The mass percent is simply the mass of that element divided by the total mass of the sample, which I would know when I would measure that before I put it into the furnace. And so I can get the mass percent for carbon, I can get the mass percent of hydrogen. And if I add up the 2 masses of carbon and hydrogen, and that mass is less than the original mass of the sample, then there must be some additional element. In many cases, that's oxygen, or it could be something else. But the mass percent of whatever that third element is simply the total mass of the original sample minus the masses of carbon and hydrogen that I've determined, and then divide that number by the total mass to get me the mass percent of whatever the third element happens to be. Of course, it can get more complicated. We could have 4 or 5 elements present in a molecule, but in many cases, we only have at most 3 elements present. So this is a very useful tool for determining the mass percent of each of those elements. Let's do a practical example of this. And then in the next video, we'll work through how do we take mass percent and determine a molecular formula or an empirical formula from that. So here's the example. Valproic acid is a material that's commonly used to treat seizures and bipolar disorder. And it's composed only of 3 elements, carbon, hydrogen, and oxygen. My original sample mass was 0.165 grams. And I combusted that in the chamber to produce 0.166 grams of water and 0.403 grams of CO2. What's the mass percent of each element then in valproic acid? Well, I follow my formula for determining the mass of carbon and follow the formula for determining the mass of hydrogen in the original sample. I can start with CO2, my mass of CO2, and first convert that to moles of CO2 using the molar mass. Then I know that there's 1 mole of carbon for every 1 mole of CO2 because there's 1 carbon atom for every 1 CO2 molecule. So I've converted from moles of CO2 to moles of carbon. And then I can convert from moles of carbon back to mass of carbon by multiplying by the molar mass of carbon, or the atomic weight of carbon, just 12.0 or 12.01. If I multiply all of this through, then I can come out with a mass of carbon in the original sample. I can determine the mass percent simply by taking this mass and dividing it by the original mass and multiplying by 100%. So I come out with 66.6% carbon in valproic acid. I can repeat the same process for hydrogen and using the mass of water, convert the mass of water to moles of water. I just have to pay attention that there are 2 moles of hydrogen for every 1 mole of water because there are 2 atoms of hydrogen for every 1 molecule of water. And then when I'm converting from moles of hydrogen to mass of hydrogen, I simply use the atomic weight of simply hydrogen, not H2, just of hydrogen. I come out with a mass of 0.0186 grams of hydrogen, and I can figure out the mass percent of hydrogen from there as well. Now, assuming that my total mass percent has to be 100%, and so I can simply take 100% and subtract the other mass percents to get me the percent of oxygen that is remaining. And this is how you would use combustion analysis to determine the mass percent values of elements in a compound. In the next video, we'll talk about how to use this mass percent information to determine a formula for the chemical in question.